An additional colligative property that you may have run across at some point in your lives or your experience is osmotic pressure. Now, let me explain a little bit what that might entail. Let's imagine the following apparatus that's given here on the left-hand side, and I'm going to say that this system is under an atmospheric pressure of P. And on the left-hand side of this, I've got water without any solute in it. And on the right-hand side, I've got a concentrated solution of some kind with a solute, which I've colored red. Now, if I place a semi-permeable membrane between those, and this is a membrane that will allow water to pass through, but not the solute particles on the right-hand side. So in other words, I can't get any movement of the red stuff through this way, but I can get movement of water through this way. All right, what will happen over time is we'll observe basically that the water level will go down and the solution side level will go up. And so it'll form a more dilute solution over on the right-hand side. And on the right-hand side, we'll end up having a hydrostatic pressure. I won't define that, but I think you can probably imagine a hydrostatic pressure of pi, okay, in addition to the atmospheric pressure of P. So the total pressure on the right-hand side is going to basically be the atmospheric pressure plus the hydrostatic pressure. All right, and so what we want to do is understand where osmotic pressure comes from in terms of some of the thermodynamic quantities that we've gotten acquainted with. Now, I'll point out that this is an equilibrium. So on the left side, I'll have something that will represent the chemical potential of the pure water. I'm going to assume that the solvent is water in this case, so the component 1 represents water. And it's at some temperature and pressure, and that temperature and pressure aren't going to change during the course of this process. And that when it reaches equilibrium, say over here for this figure, the right-hand side would be given by the water in the solution. Now will have the chemical potential of temperature and a total pressure of P plus the hydrostatic pressure. And we'll also have some dependence on the chemical activity on this side. All right, so this would be how we would typify the equilibrium position that we have reached during the course of this osmotic process. Now I can also write the thing that's over here on the right-hand side as we have in the past, as a function of the pure solvent plus RT times the log of the activity that's due to the solute. So this again is something that I'm writing for the right-hand side. This is the pure solvent contribution to that chemical potential, and this is the solute contribution to that chemical potential. So this is due to the solute effect. So what we're interested in doing is characterizing these solute effects in terms using the chemical potential and using those characterizing those solute effects as how they change the pressure. So we're looking at how the pressure varies with these effects. So one clue we have for this is that the chemical potential itself is a function of the pressure. And we can quantify that function in the following way. If I have a pure substance and I take the derivative with respect to the pressure at some constant temperature, that's just the same as taking the derivative of the molar volume with respect to the pressure at that constant temperature. And I know that that's going to give me the molar volume of the pure substance. Now in this case, I'm talking about the solvent, so I'm going to use water, and I'll give it the index 1 just to emphasize the fact that I'm really talking about the solvent here in terms of this molar volume. Now, when I go from one of these, when I go to the initial state to the final state, so this is time passes. So in essence, this is my initial state, and this is my final state over here. I'm going to have a change in this chemical potential. That change in the chemical potential of the water could be written, in effect, as its final chemical potential, which is this thing here, temperature, pressure plus hydrostatic pressure, minus its initial value, which is this thing here, of just the water at temperature and pressure. Okay, now I can use this relationship that I've encapsulated up here to relate the difference between this term here and this term here as equal to minus RT log of the chemical activity of this solution. All right, so this is the game plan that we're going to use to get that, and we're going to try to evaluate this delta mu, this chemical potential change, by using this relationship for how it changes with pressure. All right, so the way we would get that is we would determine delta mu. It's a state function, so we could determine it by integrating over d mu, and in this case we'll be integrating it over d mu dp at constant temperature dp. Now I'm going to make p prime be my integration variable, because what I'm going to do is I'm going to integrate this from an initial pressure of p to a final pressure of p plus pi, the hydrostatic pressure. All right, so this will give me an idea of how this chemical potential changes for the water in its pure form and in its solution form from beginning to end. So when I write this out using this identity for the partial derivative, I'll end up with an integral that looks something like this. I'll have v1 star dp prime. Okay, a fairly simple, innocuous looking thing. But now I want to say something about this solvent or water. Water is a pretty incompressible liquid, as are most liquids. So we can, to I think a reasonable approximation, assume that it stays constant. So in other words, we're going to make this assumption that the pure liquid is constant molar volume, okay, independent of pressure. So I can pull it out of the integral sign. This will leave me with this kind of integral. And this is an integral I hope that we can all do, because it's just dp prime. So I'm going to end up having V, the molar volume of the pure liquid, times the difference of these two. And I think we can easily see that the difference between these two is just the hydrostatic pressure. So I'll end up with this final result. Okay, well that's great, because now I'm going to relate it to my activity. Okay, but once again, for the activity, I'm going to approximate that as negative times the mole fraction of component 2. Okay, mole fraction of component 2 is just N2 over N1 plus N2, but we'll assume that the amount of the solvent, in this case water, is much greater than N2, so this is in effect going to be equal to negative N2 over N1. All right, I have a negative sign out front here, so in fact I'm going to have my final result here, or well, my semi-final result here, is equal to N2 over N1 times RT. Okay, because I've made this approximation that log of A1 is simply negative of the mole fraction of the solute that's present here in the mixture. Okay, now I also want to identify N1 times the molar volume of the pure liquid. Okay, well N1 is the number of moles of the pure liquid, and this is the molar volume, so in fact this is going to end up being just the volume of my sample. All right, so once I get through with all of that, I divide both sides by the volume, I will end up with an equation that looks something like this. I'll be able to relate the hydrostatic pressure that results from this solution as equal to N2 over the total volume times RT. But now this N2 over the total volume, that's just moles per liter. So that's in effect the concentration of the solution, where concentration is in molarity. All right, so this gives me a nice compact expression for quantifying the osmotic pressure, the hydrostatic pressure that results from this solution in terms of the concentration of the solution and the temperature.